So that brings us to our final section of Calculus 1 at Bellevue University, which is finding the integration of the inverse trig functions, section 5.8 of your text. Again, I've just split this into 2 parts rather than 3. This review of the basic integration rules is really just part of the one from before that says, just remember that we know how to do all of the types of integration now. So we're going to integrate trig functions whose antiderivatives involve inverse trig functions, which should look super familiar. A little bit harder than the last section because now we have to use those functions that we learned to make sure that our equation fits the pattern. Which pattern does it fit? So have that same handout that you had handy in our last section handy for this section. And then I want to talk to you about how to complete the square to integrate a function. So again, what I would suggest to you, have that handout in front of you. We'll again point out that this is the format that I would use for arc sine. So this is the derivative, obviously. Since we're doing the integral in this section, I'm going to be integrating something that's in this format. So it's good to, again, remember that arc sine and arc cosine are the same, except for arc cosine has that negative in front. So again, we're really just dealing with 3 pairs. So if you want to have these memorized to make things go quicker for you on your homework and your final, etc., that's fine. Or just make sure that you have a handout or something to refer to. So again, you can either keep the handout from the last section in front of you, or here is the abbreviated version that says, hey, if I'm integrating, here are the patterns that I'm looking for, and what those patterns then will equal. But again, if you understood section 5.7, this is the exact same thing. It's the same idea. I'm looking at making sure things fit a certain pattern, and then this is my final solution. So let's take a look. So again, if I'm integrating, here I have find the integral of essentially 1 over radical 4 minus x squared. So what I know is that u is always going to be something that includes a variable. So when I'm looking at this guy is u squared. So if x squared is u squared, then u must be just x. That's where I got this. The number, the one that doesn't have a variable with it, is always an a. So 4 is a squared, so a must be 2. That was really weird too that I just wrote. So a must be 2. As usual, I'm then also going to find du, because that's going to be part of my pattern. So the derivative of u in this case is just dx. 1 dx or just dx. So now, having defined u and du and a, essentially I can rewrite my original integral as the 1 over the square root of a squared minus u squared du. Well, now I just have to go back and look at my handout that says, if it fits this pattern, then my solution is the arc sine of u over a plus c. Well, now I'm just going to plug back in u and a. So it's really as easy as that. It's all about patterns. Again, memorize them if you want, but you don't have to. Here are 2 for you to try on your own. Again, I encourage you to have that handout in front of you so that you know, once you get it in the correct pattern, what are we looking for. When you are done, press play to check your work. So again, the first thing I would do for the first question is know that this is a value that doesn't have an x. So that means a squared is equal to 2. That equal sign looked like a minus. A squared is equal to 2, so a is radical 2. And u squared, which is the one that has the variable with it, is 9x squared. That means u must be 3x, and du must be 3 dx. So that's my very first step. Then I'm going to rewrite it using all of the substitutions. So dx, I'm going to need 3 dx essentially, so it's 1/3 and 3 dx, which is du. And then 2 I'm replacing with a squared, and 9x squared I'm replacing with u squared. So then I say, well, what pattern is this? I look back at my handout. That pattern is the arctangent pattern, and the arctangent pattern says do this. Take 1 over a, so a is radical 2. Notice I've written 1 over 3 radical 2 because I've also taken it times the 1/3 that was on the outside. And then arctangent of u over a, so u is 3x, a is radical 2, and then plus c, that's my final answer. I don't need to get too crazy with making sure the radical is not in the denominator. I really don't care that much. So I would leave it just like this. Same thing for the next one. Again, I'm looking at what each value is. So my u would be the square root of 4x squared, which is 2x. My derivative of u would just be 2dx. My a would be 3. And then using all of those substitutions, it fits this pattern, which is the arcsecant pattern. Then all I'm doing is plugging those values back in the appropriate spots. Here are a couple more practice. Again, one of them I threw in a transcendental function just to make sure you're paying attention. Try both of these, then press play to see how you did. Again, the whole process here is all about being able to properly define u, du, and a, and then match it up to which one it should go to. So here, this obviously is going to be my u, so I'm taking the square root of that, which is x radical 2. And then I'm taking this guy and calling it a, so the square root of that is 4. And then of course du is just the derivative of u with respect to x. That leaves me with this, which of course I could have written as the integral of du over u radical u squared minus a squared. That fits my arcsecant pattern. This is what I'm going to plug back into my arcsecant pattern. So I did that, and that's my solution. Same thing for this last one. This guy, the square root of this guy would be u, so that's the square root of e to the 2x is e to the x. Du is e to the x dx. A is the square root of 2, so that's radical 2. Then I can rewrite that as an integral with the du's and the u's and say which pattern is that? Well, it's the same pattern I just used before, arcsecant, so plug everything into the appropriate spots and get my final solution. You might also end up with an example that doesn't fit any of our patterns. So obviously if I started with this one, I would say a must be 2 and u must be x. And that's all well and good, except that the numerator doesn't fit and I can't make it fit. So notice all I did was I kind of cheated a little bit and I said, let's integrate it by parts. So let's take 2x over that and let's take 4 over that and integrate each one separately. And so for the first guy, if you'll notice, this just fits a normal integration pattern. So I didn't have to use any inverse trig functions on this one because it actually didn't fit any of the patterns. I said u is the whole thing, 4 minus x squared. The derivative of that is negative 2x, so really I can rewrite the first one as 1 over radical u, or u to the negative 1/2 du. So because that works, then when I integrate, I'm just doing normal integration. However, on the other one, my other part, notice I'm just using v instead because it's two separate parts, u and du, so I'm using v over here, but it doesn't matter. V is equal to x because that's the square root of x squared. the square root of 4 is 2. So on this side, I am going to use one of those inverse trig functions, which happens to be arcsine, and then just do my normal substitution.